the younger people in this class, by the time you grow up and you have your kids, they won't be playing games on mobile devices anymore. They won't be addicted to computers games as we know them. Okay, they'll be in virtual reality. In other words, you will see them wearing a goggle or Google Glass type of device all day long, and they'll just be going like this.
Or just a virtual helmet kind of thing.
Damn! That's the way they will be. They won't be looking at a screen at all. Yep.
Have you seen the Oculus Rift?
Yep.
Yeah, it's like a virtual reality.
Yep. It's still at its infancy stage because when you look at those devices right now, they're really big and bulky and doesn't look very attractive. But that technology, I mean, if you look at laser printers, okay, the first laser printers were like the sizes of refrigerators, right? Costing $3,000-$4,000 at the time, which means that they're very expensive. And these days you can go into Fry's, spend $60-$70, get your laser printer, and it hardly weighs anything, right? I mean, you pick up the box, it's like, are you sure there's a laser printer in it? And so, yep.
I did that down in Austin, Texas, where they had the virtual reality go-karts, and they were shooting Mario Kart. So they were driving around in the go-kart and playing Mario Kart.
Is it stereo vision or is it still flat?
It was like the Oculus Rift thing where you wear the virtual reality on your face, but you're driving a go-kart.
Yep. Now, when you hit something, does it give you a jar? I mean, is there anything to give you a jar?
Oh God!
I didn't get to experience it.
You get hit with one of the items.
Mm-hmm. Yep. Well, but that's where things are going. I mean, that's where technology is going. We won't be seeing screens anymore in a class. All of you guys will be wearing your VR glasses. You won't even be in a classroom because when technology is that good, we can have a virtual classroom, and it will appear that I will still be standing here and you will still be sitting there, but it's not really real anymore. I mean, everything is just virtual at that point. But the best part is, unlike online classes now, the technology would allow you to do live interaction with the rest of the class and also the professor, as opposed to, I don't quite understand that concept on this web page. I'm gonna write my email to my professor, wait half a day for the reply. It's going to be much more interactive. All right, so that's going to change a lot of things, as far as I know. Yep. All right, so I think the recorder is on already, so that's good. And then we'll go ahead and close all this stuff, and we'll start with the exam. Okay, this is what I call the rub salt on wound session. But salt does one thing good on wound. Well, it stops the infection. And that's basically what it is for me. I want to make sure that we go over the answers, and so that people who may not get everything right at least will know what is the correct answer. And for the most part, you can kind of guesstimate your score, or how well you're doing in the test as a result. So I'm going to start with question 1 in the exam question. I'm going to do every single question on the projector, so even though you don't have your exam in front of you, it's going to be okay. There are variants of the questions, so if your question is not exactly what you see on the projector, it should be similar, but not exactly the same. So the same approach would work, for your particular question. Okay, the first question is a trace question. And it goes like this. X gets initialized to 0, Y gets initialized to 2, while Y is greater than 0, do the following. X gets X plus 5. Some people may get X gets X plus 4 or some other number. If X is greater than or equal to 6, then, so some people may get a different number to compare to. X gets X minus 6. Y gets Y minus 1, and if, and while, and that's the entire pseudocode. And I'm just going to fix the indentation first. So, all right. So we have the pseudocode here. Are there any questions about the pseudocode itself before I start tracing it? No questions? Let's go ahead and trace this algorithm. All right. I still have. This is from the earlier class. I'm going to close it. So with the second view, I'm going to look at the trace only. So when you look at the trace, in this case, the trace already gives you the columns that you need. One is the comments, one is line number, and one column for X, one column for Y. So those columns are already pre-allocated for you. So now I'm just going to replicate all of that stuff here. The first line is the precondition, and in this case, X and Y are both unknown to begin with. I did not ask for any assumptions, so they have to be unknown to begin with. On line 1, X gets initialized to 0. On line 2, Y gets initialized to 2. On line 3, we have a while loop. Y is greater than 0 is true because Y has a value of 2 at this point. Then we move on to line 4, the first line inside the loop itself. We add 5 to X. X goes from 0 to 5. On line 5, we evaluate the condition. X is greater than or equal to 6 in this case is false because it is just 1 short of 6. So where did we go next? That really is one of the biggest questions is where do we go? We go all the way back to line 3. Because at this point when the condition is false, that means we do not have anything to do with the conditional statement. The conditional statement does not have an else branch. And as a result, we are done with the conditional statement, but there's nothing else after the conditional statement. It is the last statement inside the loop itself. So when we're done with the last statement in the loop, we go back to the beginning to reevaluate the condition. So that's why we're going back to line 3 and reevaluate Y is greater than 0. It is still true. So this transition to me is far more important than the transitions from line 1 to line 2. That one I'm not even giving any points. I mean that's just sequential. Line 2 to line 3, sequential. Line 3 to line 4, kind of not so sequential because you do have a chance to get out of the entire loop on line 3, but it's not as important as the transition from line 5 back to line 3 because that really is the first the big question. And I think I got it right. Okay, so now we're back to line 3, and the condition of line 3 is still true. We go back onto line 4. Line 4 is just blindly adding 5 to X, so X now has a value of 10. And then we go to line 5 again. But this time on line 5, X is greater than or equal to 6 is true, and as a result, we have to execute the then branch of this conditional statement, starting on line 6. On line 6, we subtract 6 from X, so it goes from 10 back to 4. Sorry?
Yeah.
Okay. And then on line 7, we subtract 1 from Y. Y goes from 2 to 1. And then at this point, we are done with the then branch of the conditional statement. And that means we have to get out of the conditional statement. The conditional statement itself is the last statement of the loop, which means now it is time to go back to the beginning of the loop, which is on line 3. So this transition from line 7 to line 3 is also an important one because you have to understand the structure of the code to make this transition. Back to line 3, Y is greater than 0 is still true because Y has a value of 1 at this point. We go back to line 4. Line 4 is just adding 1 to X. X goes from 4 to 9 in this case. We go to line 5. The condition is X is greater than or equal to 6. It is true because X has a value of 9 at this point. We go to line 6. We add 1 to, we subtract 6 from X first, so it goes to 3. And then on line 7, we subtract 1 from Y. Y goes from 1 down to 0. And at this point, we have to go back to line 3 one last time. Okay, we cannot get out at this point because we have to get back to line 3 to evaluate Y is greater than 0 being false. Then we can get out of the loop. So this would be the actual trace of this algorithm. Are there any questions about this trace? No questions? Okay. If there are no questions about this trace, we'll move on to question number 2. Question number 2 is, I would imagine it's easier than this one, but some people may disagree. All Alright, so let's go ahead and look at the algorithm first. The algorithm is x gets initialized to 0, y gets initialized to 0. Repeat, x gets x plus y plus 1. Y gets y plus 1 until x is greater than or equal to 25. And your boundary may be different. In other words, in your test, you may have a different initial value for x, and you may have a different terminating condition. But it works out pretty much the same way. It should have the same number of iterations. All right, so let's take a look at this one. Did anyone notice any pattern as far as the values of x and y are concerned? Yep.
Y went up by, I believe, 1 every time.
Say again?
Y went up 1 every time.
Y goes up each time. What about x? Does x and y have any relationship? Nope, it's not 2. Okay, let's.
It's like this.
Yeah, it's
squared, right?
Squared.
Yeah.
Yep. Y is x is y squared at the end of each iteration.
Yeah.
Yep.
Interesting.
It's because of the quadratic equation. All right, so let's take a look at this one, and we'll look at the trace. We have comments, y number, 1 for x, 1 for y. Precondition, both can be unknown. If you specify any specific value here, I'm not going to take any points off, but if you leave it blank or not have a pre-line, I'm going to take some points off. Okay, because you have to state a precondition. It's just that if you specify this to be 25, it doesn't matter because I'm going to overwrite it in the next 2 lines. So that's why they should start with unknown values. On line 1, x gets initialized to 0. On line 2, y gets initialized to 0. We don't trace line 3 because it's just a marker to mark the beginning of a repeat loop. So the next line to trace is going to be line 4. Line 4 in this case is 0 plus 0 plus 0 plus 1, which means it ends up with a value of 1. And then on line 5, y becomes 1. And on line 6 has to be traced because line 6 actually has something to do. First of all, it has to evaluate the condition x is greater than or equal to 25 is false, and then it has to make a decision where to go next. Am I supposed to go back to the beginning of the loop, or am I supposed to exit at this point? Well, in this case, because the condition is an exit condition, we have to go back to line 4, which is the beginning of the loop. So line 6 has to be traced in this particular question. All right, so at this point, most people might look at this and go like, wow, it's going to take a long time to get to 25.
No.
Well, it's not going to be as long as some people think. It still takes a few iterations, but it's not quite as bad as most people think. Okay, now since x and y are both 1s, so now we have 1 plus 1 plus 1 plus 1, which is 4. And then on line 5, we just add 1 to y goes to 2, we go to line 6, x is greater than or equal to 25 is false. Then we go back to line 4 again. This time it becomes 4 plus 2 plus 2 plus 1, which is 9. And then on line 5, y becomes 3. And then we go to line 6, x is greater than or equal to 25 is still false. So we go back to line 4 again. 9 plus 3 plus 3 plus 1 is 16. And then we go to line 5, 3 plus 1 is 4. So the square relationship is maintained throughout all iterations of this loop. X is greater than or equal to 25 is still false, but only for one last time. Because on line 4, now we have 16 plus 4 plus 4 plus 1, which is 25. And then on line 5, we add 1 to y goes from 4 to 5. And we have to go to line 6 before we get to post, because line 6 is really the only line that can make that decision. When the condition is true, then we can exit the loop and then go to post. Are there any questions about this one? No questions? Okay. The reason why we see the square relationship, yep, go ahead.
Why did you use repeat instead of while?
Just a different type of loop,
Okay.
yeah. Okay, so the question is, why does this work out? It has to do with, x plus 1 squared. The square of the next number is the square of the current number plus 2x plus 1. It has to do with this equation. So when you express this, it becomes x squared plus x plus 1. I mean, x is actually taking the role of y in the question, but that's why it works out. Okay, which also is a kind of a neat way to find if you're always going up in the pseudocode. If you're always going up just by 1, in terms of the number y, but you always want to keep track of the square of that number, that means to get to the square of the next number, there's no need to use multiplication, because if you look at line 4, it only has additions. It is not a main issue when you're dealing with Pentium processors that have hardware multipliers, so multiplication is really fast. But when you have a smaller and less expensive processor that does not have hardware multiplication, that can be a costly calculation. Calculating the square of a number can take a long time. So when you do this trick here, it basically turns a really long multiplication process into a very short, 3 additions is basically what it is. Okay. What kind of inexpensive processor are we talking about? Something that you can buy for 50 cents. Or something that can fit inside, like a Fitbit. Okay, they probably have a processor of some kind on it, but because they have to save power, they cannot have a powerful processor. Because any type of powerful processor, even if you clock it down to a lower clock, it still has a lot of transistors to go through transitions, so it cannot be running at very low power. So for anything that would fit into this type of application, that one charge can last a week, you're looking at an 8-bit processor at the most. Okay, not even 16. You're looking at an 8-bit processor with limited hardware resources, and that's when things like that, tricks like that, can become useful. All right, let's move on then to the second question. Oh, the third question. This is our second one. The third question is, according to my previous class, the Ninocore class, that's their least favorite question.
Yep.
That's the one with the indentation first, and then you have to trace it after the indentation. So we'll take a look at it. All right, so let's first deal with the original program. We'll do the indentation, and then we'll, while x is less than 7, do the following. You might see a different version of this, slightly different variant of this. If x is greater than or equal to 1. And this is a hard one to type, because I have to track which line I'm typing. Except for the line numbers, because I missed one line. So I went up to line 14, and then there's no line 15, and then we have line 16 and line 17. So I think that's how it looks like in your test. There we go. All right, so the first thing we have to do is to fix the indentation, because currently it has no indentation. Without any indentation, I can still trace the program, but it's a lot harder. Okay, even though I can follow the logic, I have to visually scan for the end if for a particular if, and look for the beginning part of an if, and so on and so forth. So even for me, it really helps to do the indentation first. So we'll go ahead and do it first. There are 2 ways to do it. You can do it from the inside out. You can do it from the outside in. You can add, the parentheses as a trick, so that you can track, how many levels of indentation we're dealing with on each particular line. So for me, I just look for, I just sequentially scan it until I hit the first thing that has a nested structure, which is on line 2. A while needs to have an end while. This is the easy one because we only have one while loop here, so it's easy to spot the while and its end. So everything inside the while loop they will all need at least one level of indentation. So I fix that first. Okay. So for you can just add, like vertical lines on the side to indicate how many levels of indentation you need to add before you copy the lines over to the other side. Now I look at this code here and I say, okay, if also has an end if somewhere. So now the question is, how do I find the end of this particular if? Okay, this is an open, close, which means I'm back to one open. This is another open, a close. Now I'm back to only one open. So this is closing line 3. In other words, line 3 is closed by line 16. Now I have to also look at, does it have an else corresponding to this if here? What do you think? Yes. The else is on line 10. Okay, so that means these 3 lines they form the skeleton of the outer conditional statement, which also means all of the other lines from line 4 to line 9, and then from line 11 to line 14, they all have to be indented again. So from line 4 to line 9, which is the then portion of the conditional statement starting on line 3, and then from line 11 to line 14, which is the else of the conditional statement starting on line 3, these will require one more indentation. Now I go into this portion here and say, okay, is there anything else that is nested here? Yep, because on line 4 to line 8 is a conditional statement, and within this conditional statement, line 5 and line 7 need to be indented because one is the then portion and the other one is the else portion of this conditional statement. When I look at line 11 to line 13, it is also a conditional statement, and as a result, line 12 needs to be indented because that is the then portion of that conditional statement. So now we have the correct indentation of the entire algorithm. Are there any questions about this part? How long did it take for you guys to do the indentation?
Not too long.
It's okay? Took a little bit of time? But did you have a right? But did you guys have a systematic way to do it? That really is the most important question.
Yeah.
Because as long as you have a systematic way of doing it and you can track, all of these things, it becomes a matter of time. It's just mechanically, okay, I did copy this. But without a systematic way of doing it, then it becomes a much tougher problem because now you have to look at it and go like, but how do I figure out where's the end of this thing? How do I determine the level of indentation of this line? So that becomes a much harder problem if you don't have a systematic way of doing it. All right, so now that we have the actual code, we'll go ahead and trace it. Well, the code with indentation. Right, so let's resize this just a little bit. Okay. So we have comments, line number, and we have a single variable, in this case x. The precondition is we don't need to know anything because we're going to overwrite it with line 1. Line 1 just overwrites x with 0. Let me just kind of make these columns closer. Okay. On line 2, we have the beginning of a while loop. We evaluate the condition, x is less than 7 is true because x has a value of 0. And then we get into the loop starting with the conditional statement. And the funny thing is, it only has one conditional statement inside the loop. Okay, all of the other 2 conditional statements are nested within this one. As far as the loop itself is concerned, it only has one statement inside it. It just has, it's just like a big folder having another folder in it. Okay, but that embedded folder has, a bunch of other stuff in it. So we go to line 3 because line 2 has a condition that is true. On line 3, we evaluate another condition. X is less than 3 is also true because x has a value of 0 at this point. So now we move on to line 4. On line 4, we evaluate is x greater than or equal to 1. That is not true. That is false. So we have to look for the else branch, and in this case, there is an else branch corresponding to the the conditional statement starting on line 4, and the else branch is on line 7. This transition is important, or more so than the other transitions, because we need to locate the else branch of a conditional statement. On line 7, we are adding 2 to x, so x goes from 0 to 2. And then where do we go?
9.
We go to line 9. Okay, because line 7 is the only line inside the else branch of the conditional statement. So when we are done with line 7, we are done with the entire conditional statement. Line 9 is sequential to the conditional statement, and that's why we have to continue with line 9 at this point. Line 9 is just adding 1 to x again, so x now ends up with a value of 3. And then where do we go? This transition is also important. It's actually one of the most important ones.
Back to line 2.
We got back to line 2, because now we are done with the entire then branch of the conditional statement starting on line 3. When you're done with one branch of a conditional statement, you're done with the entire conditional statement. So we have to get out of the conditional statement. Line 16 marks the end of this conditional statement that we are ending at this point. But there's nothing after line 16. We don't track line 16 either. So that means we're done with one entire iteration of the while loop. It is time to go back to the beginning, reevaluate the condition, and see whether we have another iteration to perform. So this is why we have to go back to line 2 directly from line 9. And once again, this transition is important. So now we reevaluate whether x is less than 7. X has a value of 3. It is still less than 7, so this condition is still true. We go to line 3. X is less than 3 is false this time, because x has a value of 3. So when the condition is false for this conditional statement, we have to go to the else branch if there is one. Is there an else corresponding to line 3? Yep. Well, with the correct indentation, it is easy to see that line 10 has the same indentation level as line 3, so that really marks the beginning of the else branch of the conditional statement starting on line 3. So that means we continue our trace on line 11. So this is also a kind of important transition because we're going to the else branch. On line 11, we have the condition of not x is greater than or equal to 5. Is that true or false? X has a value of 11. 11 is greater than or equal to 5 is false. Not false is true. Okay, so that condition is actually true, which means we execute a then branch. It only has a then branch. On line 12, x gets incremented by 2, and then we get out of the conditional statement. It ends on line 13, but there's an assignment statement, line 14.
Isn't x supposed to be 5?
Oh,
Because it went from 5.
yep, you're right. Okay, so x becomes 5 because we're adding 2 to 3, and now we end up on line 14 because we're done with the conditional statement. Line 14 is sequential to the conditional statement starting on line 11, and that's why we have to execute it too. X gets x plus 1, which is 6, and now we are done with the entire conditional statement starting on line 3, so we have to go back to line 2 again. X is less than 7 is true for the last time, and then we go to line 3. X is less than 3 is false. We go to line 11. Not x is greater than or equal to 5 is false this time, because x is greater than or equal to 5 is true, not true is false. So this is now false. There's no else branch corresponding to this conditional statement. That means if the condition is false, I got nothing else to do for the conditional statement. So now we continue execution on line 14. On line 14, we just add 1 to x. X goes from 6 to 7, and then we go back to line 2 to figure out that x is less than 7 is false. Then we go to post. And that concludes the trace. Are there any questions about this trace? Questions? Takes a little longer, you know. It has the same number of rows as the other two traces, almost the same. But this one is more involved because you have to find out. It's not nearly as sequential. I mean, it's not linear as the other ones. All right. So this one is done. And we're moving on to the last question. And I was surprised in the previous class, most people did not find question number 4, the pre-post condition, to be particularly difficult. I think it might have to do with it being very similar to the homework assignment. I was just kidding with my previous class. They can take a screenshot of my solution of the homework assignment, white out, the portion that is not the same as the question here, and just fill it in, with the stuff that is specific to this question. Because the framework, the structure is almost the same. The ordering is off a little bit, but otherwise, it's the same concept. 2 forget operations, 2 substitution operations, right? So we'll start with that one. I'm going to use a word processor for that purpose. All right. So, and I'm going to change the view to a web layout, so this way we don't have the margins to deal with. All right. So I'm going to give you. You might see a slightly different version depending on which variant you get, but they are all very similar in this case. So we have x gets j as the first statement. On line 2, we have x gets x times 2. On line 3, we have y gets x. And on line 4, we have y gets y plus 3. Okay, so you might see something slightly different, but it will just be a minor change compared to this one. The precondition of line 1 is just true, which means we know nothing about the variables. And now we want to move on. Derive post 1 from pre 1. So on line 1, I define f of x, the function, to be just j, because x is on the left-hand side and j is the right-hand side. We identified it has no inverse. If you mentioned that the right-hand side does not refer to the left-hand side, even better, but no extra credit for that, unfortunately. But you do have to make the conclusion that there's no inverse function. Okay, there's no f prime for this particular function. And as a result of that, we use the forget operation. When you apply the forget operation, the post condition of line 1 is based on forgetting something from the precondition of the same line. Anything that we know about x may not be true anymore, so let's forget all of those things. But at the same time, we know one extra thing now. X and j must be the same at this point, right after the execution of line 1. And once again, we do not use a left arrow in place of the equal, because the equality symbol means we know that x equals j. We are not making x to be the j. The operation of x gets j is not true or false. It is just doing something. It is not a condition. This is a condition. X equals j is saying, okay, is it true or is it false? In this case, it has to be true because it is the post condition of a conditional statement. All right, so the next line is just expanding pre-1. So we say forget pre-1 is true, and then we perform the actual operation. True does not mention x at all, so we can keep it. And if you want to carry this one more step, which is x equals j, that's fine with me. Okay, so that means if you stop here, it is considered a correct answer. If you push it one more step to give me this answer, that is considered correct as well. So you don't have to do the simplification, but if you do it, even better. Are there any questions about step 1? Yep.
What if we went straight from, what if we skipped true and x equals j and just went x equals j?
You mean skipping this line here?
Yes.
That'll be fine. All right, so now we have to say the precondition of line 2 is the post-condition of line 1. If you say because they're sequential, even better. On line 2, now we have to say f of x is 2x. If you want to keep x times 2, that's fine. I just want to save a little bit of time here. It does have an inverse function. The inverse function is x divided by 2, and because there is an inverse function, we use the substitution operation. The way you apply the substitution operation is you start with the template itself. The precondition is inside the substitution operation, and then whenever we see x, we replace it with x divided by, whoops, not yet, with f prime applied to x. That's why we need to find the inverse function, because we stick the inverse function inside the substitution operation. And then in the next line, we actually expand it. So in this case, the precondition of line 2 is just x equals j. We look for x, and then for each time we find x, we replace it with x divided by 2. And so after the substitution, we just end up with x divided by 2 equals j, and that would be the answer for line 2. Are there any questions about the post condition of line 2? if you take it, if you do any type of algebraic operation and say x equals to 2j, that's okay too. It's not required. All right. So at this point, do we know what is x and what is j? No, we don't. We know how they relate. We know that one is twice the other one, but as far as the exact value of each one, we don't know yet. Okay, which is okay, because we still know something about the variables, even though we don't know their exact values. All right, moving on to line 3. So on line 3, we have f of y, because y is the variable on the left-hand side, equals x, which is the right-hand side expression. And there's no inverse because the right-hand side does not refer to the left-hand side. Use the forget operation. So in this case, post 3 is based on the forget operation on pre-3. Everything that we know about y we should forget. And then after this, we know one thing. We know x and y have to be exactly the same at this point. So now we expand what we know about pre-3. Pre-3 is just x divided by 2 equals j. And as a result, there's nothing to forget because x, j are the only two variables referred to by the precondition. Since there's nothing to forget, we keep the entire thing. X divided by 2 equals j. And on top of that, we also add that x and y are now the same. Are there any questions about line 3? I forgot one little thing. Just forgot to say pre-3 is post 2, because otherwise I cannot find out what this thing is. All right, last step. Pre-4 equals post 3. And I'm just going to copy and paste line 4, just so that we can see it when we work on it. All right, so on line 4, we define f of y to be y plus 3. And there is an inverse function. F prime of y is y minus 3. And as a result, because there's an inverse function, use the substitution operation. When you apply the substitution operation, you just give me the template first. And then you expand everything that you know about inside the parentheses. So pre-4 is x divided by 2 equals j, and y equals x. We look for occurrences of y, replace each and every single one of those with y minus 3. And then we actually perform the substitution operation. X divided by 2 equals j, nothing needs to change because it does not refer to y at all. The second one does need some change because y refers to y is y, so it has to be changed to y minus 3 equals x. Like so. And that becomes the post condition of line 4. Are there any questions about the derivations up to this point? All the different steps? Okay, but that's only one part of the question. There's a little bit of a second part of a question. The second part of the question, at least for this one, is after finishing line 4, y ends up with a value of 7 exactly. Deduce the values of x and j using post 4. So that means our post 4 is a little bit longer now, because it has everything that we knew about it before. And on top of that, we also say that, hey, we can actually observe and see that y equals to 7. So the question is, can we solve the other variables because we know x, because we know y has a value of 7? What do you think? Yeah, we can do it. So because of this, it implies that x has a value of what? 4. Y has a value of 7. 7 minus 3 is 4, so x has a value of 4. Once we know the value of x is 4, we can also use it to calculate the value of j. What would be the value of j?
2.
Yep. So in your case, the numbers may work out slightly differently because I use different constants, but the way you work out the equations and the pre and post conditions would be the same.
When are we going to see your grades?
As soon as I'm done grading it. It takes a little bit of time to grade it. So it's going to be maybe Thursday. By Thursday, you'll have at least 1 or 2 questions graded. I don't grade it like, finish one person, the next person. I grade question 1 for the entire class. In fact, I do it for both classes, just question 1, and then I move on to question 2. Because this way, I would have the rubric, really familiarized, so I can easily, evaluate each one. Yep.
Roll sheet.
Roll sheet, that's right. Okay, I forgot to use this row sheet last week or the week before too, so I'm going to change the dates of the columns, starting with the second column. So just use the second column to log your entry today. There you go.
Is he?
Yep.
Did we get that physical test back? Or
Yes. Yes, we will as soon as I'm done grading it. The way I do the grading is a little bit lengthy because the first thing I do, with the first question is I will destaple, your test, run it through my scanner, so I have an electronic copy, and then I will grade it from the electronic copy. I'm not going to mark anything on your paper itself, so I will restaple it and put it back into my bag and then bring it back to you. So you will see your actual grade on Moodle, and it will be in the form of an assignment. So they're not really assignments, they're really questions or your score for your questions in the exam, but it will be in the form of an assignment, because I want to borrow the mechanism of using a rubric from the assignment grading mechanism. So you will start to see assignments showing up that is not reflecting something that you turn in electronically. It is really just reflecting your questions in the exam.
So you do them exactly like the homework assignments where you can see each.
Yep. Yep. It's going to be rubric based, so you can see for each item what is the number of points that you get and why. Yep. So I'm hoping that that's helpful, because it's not just giving you a final score like, okay, this is the number, but what does it mean? If anything less than a perfect score is not very meaningful if I don't tell you why you're getting that score. So now it's broken down into small chunks, and each chunk has its own, identifier, and say that you're getting the score because of that. This is not BizTech. Sorry. All right, so we are done with this. Are there any questions about the first midterm? How was it? Was it easy, hard, about the same level that you expect? Okay. Nothing too out of the ordinary, I'm hoping. Okay. Yep.
I was trying to look into the next class is 310
Mhm.
or is it 360?
360.
360.
CISP 360.
I don't want to get too in depth, but how does this prepare us for 360, or how will this help?
Okay. In CISP 360, you'll be programming in C++. And C++ has conditional statements, just like we have conditional statements. It has while loops, just like we have while loops. It has variables, just like we have variables, comparison operators.
Critical thinking.
Well, it has all the same elements as in our pseudocode. So everything that you learn in this class, as far as programming concepts are concerned, you can reapply every single one in CISP 360. The syntax is going to be different. But as far as the syntax is concerned, I consider that a really mechanical step. In other words, if you can come up with a pseudocode and you can trace your pseudocode and verify that your pseudocode is working correctly, translating that pseudocode from the way we do it in this class to C++ should be a fairly mechanical step that does not take you a whole lot of time.
As far as the class goes, how advanced is 360? How far does it go?
360 is typically the first programming class at a UC or a CSU. In other words, at a CSU or UC, they don't have a class like this. It's kind of like starting with calculus. With most universities, they don't have a pre-calculus class. This is more or less like a pre-calculus class where we kind of brush up the skills with algebra and some of the other math stuff that you need in order to get into calculus. I think here we might have tried for years to start with CISP 360, and it was not very successful. All right, so we'll go ahead and start with the actual lecture material, and I'm hoping that some people still remember this slide here, we talked about top-down design right before the midterm, and we were working on examples of factoring before we got interrupted by the midterm. So we'll continue with that discussion, and today we'll actually start to derive algorithms, which is directly related to cisp300 because you will have to write your own algorithm in cisp300, whereas in this class, I don't emphasize that part as much. All right, so we'll start with this one, and we'll go back and just do a few examples in terms of factoring.
This is topic 4, right?
This is, just hold on 1 second. Hello. That took a while. Okay, so I just want to point out where we are in the class. We are in topic 4 in top-down design. All right, so what we are trying to do here is we're trying to write an algorithm that can print out all the prime factors of a particular number. Okay, so what we'll do is we'll do it by hand a few times first. All right, so let's do it by hand. Let me pick a number. Let's pick 60. 60 is a good one. Okay, so I want to factor 60 into its prime factors. I'm pretty sure most of you still remember how to do it. So most of you can look at 60 and go like, oh, okay, I can spell out all the prime factors right away as in one single shot. 2 times 2 times 3 times 5, okay? Well, that's great, except it's not going to be very helpful when it comes to writing an algorithm because it's not a very step-by-step process. It's not a very systematic way to do it, okay? So what we want to do is to do it really step-by-step, even though you go like, do we really have to do it this way because I can already tell all the prime factors in this number? Okay. In other words, what we want to do is to find one prime factor at a time, and we start with a smaller one. Okay, we start with the smallest prime factor of 60. What is the smallest prime factor of 60? Just 1. 2. Okay, very good. So once we take care of 2, then we have the 2 times 30, and then we look at 30 and say, well, can we do more factoring with 30? Yep. Doing the same thing, the smallest prime factor of 30 is, once again, 2. Okay. It's 2 times 15. We look at 15 and say, what is its smallest prime factor? 3. Okay, we look at 3 times 5. And then we have 5 here. What is the smallest prime factor of 5?
5.
It's 5 itself. Okay? 1 is not a prime number. Surprisingly, 1 is not considered a prime number by definition. So now we have 5 times 1, and then we look at 1 and say, okay, we're done, because 1 cannot be factored at all. It is not even a prime number. So by the time we get to 1, there's nothing else to do. All right, cool. So let's start with another example here, 26. 26 is 2 times 13. 13 is 13 times 1, because 13 is a prime number itself. By the time we get to 1, there's nothing that we need to do because 1 cannot be factored. All right, so I think we're getting the basic idea here. Just for katas, we'll start with one that is kind of tedious. Let's try 128. 128 is a power of 2. It is 2 to the power of 7. So it is a little bit tedious, but it works out the same way. 64 is 2 times 32. 32 is 2 times 16. 16 is 2 times 8. 8 is 2 times 4. 4 is 2 times 2. 2 itself is 2 times 1. And when we get to 1, we can stop. Is that making any sense? Okay. All right. So I think in general, we can do it by hand now. The next question is, once you know how to do something by hand, and seemingly using a fairly systematic step-by-step way of doing it, how do you write it out in pseudocode so that you can have a computer to follow the logic and perform those operations? That really is a big question, and that really is one of the hardest things to teach in this class. A lot of people may think that pre and post conditions and how to do all the derivations is difficult. it may be difficult because, in terms of, just symbolic operations, they're fairly abstract, and most people may not have a lot of exposure to that things. But once you have enough exposure, Boolean algebra is very mechanical. It's really more mechanical than normal algebra. Okay, so that part is not as difficult to teach because it's just a whole bunch of rules. I mean, if you look at conjunction, conjunction is defined by what? True and true is true, true and false is false, false and false is false, and then we have one last thing, which is false and true is false. That is the entire definition of conjunction. Okay, you give me two values, I'll give you the result. That's it. So it really is very mechanical, and it's not difficult to teach that stuff. But how to write an algorithm is difficult because it's almost like how do you write an English paper? Okay, you have something to express, you have a point to make. Now the question is, how do you make that point? You already understand that point. You have your opinion, you have your argument, you have your support. But how do you present all of that stuff so that the reader can follow your logic and may be convinced by your arguments? Okay? It's the same thing with programming. You already know how to do it by hand. If I give you another number, you can work it out just fine. But how do you express the way of doing it in a way that a computer can understand? That really is the question. Okay, so this is really a difficult thing to teach, but I'm hoping that if I give you enough exposure, you will get to know the gradual process of doing it. Okay, so I'll start with revision 1 of the algorithm. In most algorithms, revision 1 is just asking this one question. Do you think this is a repetitive process? Does it involve doing something over and over again? Okay, seems like it does, right? I mean, we know it's probably not a conditional statement because a conditional statement cannot easily handle, oh, we need 4 iterations this time, 2 this time, and we have 7 this time. So a conditional statement cannot deal with these things easily. I mean, yeah, you can kind of do it that way, but it makes a very cumbersome program if you try to do it that way. So we kind of identify this as some kind of loop, and as a result, we use a construct that we don't really use in a final version of its algorithm. We just say that this is some kind of a loop. Can you kind of tell me when we get out of the loop? In other words, when you look at the 3 examples that we already have here, what is the one common thing of all 3 cases that tells us when to stop?
Stop at 1.
We stop at 1, okay? Or we can say that when the number to factor is 1, then we can stop. Is that making any sense? Because we are given the number to begin with, let's say 60 to begin with, and then we find 2 is a prime number, 2 is a prime factor of 60, and then we have 30 as the remaining portion to deal with. So 30 becomes the next number to factor, and then from that we have 15 as the next number to factor. From that we have 5 as the next number to factor. From 5 we have 1 as the number to factor. Whenever we get to 1, we can stop. So I will just express it exactly the way I described it. So I will exit the loop when the number to factor is 1. Okay, done. First revision. I mean, do you call this an algorithm? Well, surely it is not very helpful because you cannot just look at this code here and have someone, not even a person, can figure out how to do factoring just by looking at this. But you know what? This is important, okay? And I'll explain why it's important. But before I do that, I'm going to use a variable because I really hate to refer to something like the number to factor as a phrase. It's much better if we just use a variable name to take the place of that phrase. So I'll just say use variable n in this case as the number to factor. Okay. Now with that variable n as the number to factor, can I change this phrase, so that it's a lot more concise and more kind of conforming to algorithm notations? N equals 1. All right, very good. Okay. So that's my second revision. That's all I'm going to do. Okay, just introduce a variable name so that we can refer to a name without any ambiguation, and we start to use symbols instead of phrases in English. Do you see any big changes from revision 1 to revision 2, other than just the name changes and being more concise? Not a whole lot of changes. Okay. So let's go from revision 2 to revision 3. And you can see that I do not start with line 1, repeat, line 2, something, and I cannot write an English paper from top to bottom, from page 1 to the last page, just typing it out. I'm just revolving my article or my English paper step by step here. Okay, I'm just making it more clear with each revision. Now, revision 3 is important because what we are dealing with here is, hey, the condition to exit is when n equals 1. And if you look at all the examples that we had earlier, they all exit at some point. So what is that telling you? What has to happen to n in order for the loops to exit?
Equal 1.
Sorry?
Has to equal 1.
Say again?
Has to equal 1.
Has to equal to 1. But did it equal 1 to begin with?
No.
No. All right, so let's observe that again. So with every single case, n starts with a number that is not 1, not 1, and not 1, and eventually it became 1. So what is that telling you about the loop that has to do with n? It has to change n, right? Because if the loop does not change n, then n can never get to 1. And then the exit condition can never be met. Now that is an important observation because whatever you specify as the condition of a loop, at least one of those variables need to change over time. Is that making any sense? Yep.
So you start with while n is not equal to 1 to
Okay, well, at this point we don't know, I don't know whether I want to use a post-checking loop or pre-checking loop. The only thing I know is it is repetitive, so it has to be one of those two. Okay, but what I'm more concerned about is what am I doing with n for each iteration. So we want to look back at the example and say, okay, what are we doing to n for each iteration? In other words, how did we get from 128 to 64? How did we get from 26 to 13? How did we get from 15 to 5? That's the question. How did we go from one iteration to the next? What do you think happened to n? Divided by 2, divided by 3, sometimes divided by 5. Divided by a prime factor of the previous value of n. Okay. So if you want to divide n by a prime factor of its former self, don't you need to find that prime factor first?
Yes.
Okay, so let's go ahead and just write it down. So inside the loop for each iteration, we have to find a prime factor, and we'll call it f of n, so that we don't have to keep referring to that as a prime factor of n, a prime factor of n. So we can just refer to as f. Now, since the objective of the program is to let someone know about the prime factors of n, I want to print it out on a piece of paper, on the printer, on the screen, doesn't matter where, but I need to let someone know, hey, this number is a prime factor of this of the number that you just gave me. Okay, but none of this is changing n. Okay, the first one is really useful, finding a prime factor f of n. Like if you give me 30 as n, I'll give you 2 as f, okay, as a prime factor. The second line is just for output, doesn't do a single thing to n. So what do I need to do? What do I need to do to n in order to go from one step to the next? Divide n by f. Very good. Okay. In fact, I need to update n by that expression. So I'm updating n, so it becomes the quotient of n divided by f. Is that part making any sense?
What is printf?
Oh, printf is just printing the value of f to the screen, to a printer. Just let somebody know, because otherwise, the result is there, but nobody knows about it. Okay, yep, go ahead.
How is f found?
Well, that's a very good question, okay? And it's a very good question in several ways, okay? Because that really is the essence of top-down designs. Okay, at this point, we are more concerned about what we are doing as opposed to how we are going to do it. Okay, so that's a very good question. We'll come back to that question a little bit later. Okay. All right. So now that we have revision 3, we'll go for the revision 4. There are 2 revision 4s. Okay, two revisions for number 4. I will call this 4A. 4A is using a repeat until loop. It's easy to transition to a repeat until loop because we are already specifying the exit condition. So we just have to change a few words, and now we have our pseudocode algorithm. But revision 4B is going to be a little bit different. We will use a while loop to do it. So in this case, we use a while loop, which basically says as long as n does not equal to 1, do the following. And the following will be the same thing as what is inside the repeat loop here. So stash it here and put an end while at the end. Revision 4A and 4B are functionally almost the same, but not quite. The only difference is, do we test n to be equal to 1 first, or do we test it after at least 1 iteration? Which one is better? Testing it first? Why?
Trying to find the prime factor of n if n or equal.
That's correct. If go ahead.
Oh, I was going to say that if f hasn't been initialized to something else beforehand and it was right after, the way it's set up, couldn't n equal 1? Say if it was used and it goes to this without being initialized?
Right. So in the case of 4A, it cannot take care of the case when n is 1 to begin with. In other words, if someone gives me an invalid question of, can you give me all the prime factors of 1, then algorithm 4A cannot deal with it. Because the first thing it's going to do is to find a prime factor f of 1. Does 1 have a prime factor? Nope. Because 1 is not even a prime number itself, so it cannot have a prime factor. So it will be stuck. Okay, we have a problem with that. But if you look at revision 4B, it has a safeguard. In other words, if someone tells me, hey, TAC, go ahead and find me all the prime factors of 1, then I would just come back with no answer because 1 has no prime factors. It would do it correctly. Okay, so 4B is the preferred answer unless someone can tell you ahead of time and say n can never be a 1, n has to start with 2, then the 2 algorithms would be functionally equivalent. Okay, are there any questions about the algorithm up to this point? All right, so let's get back to your question of how do we find a prime factor f of n? Okay, the statement, let me just highlight that one single statement, which is the essence of top-down design here. This statement here, this is the one time when you can say procrastination is not necessarily a bad thing. Okay, because what we are doing is we're trying to keep any algorithm that we have to write simple enough that we can track everything. Okay? We are dealing with a 5-line algorithm involving 2 variables and only 1 loop. I think we can track it, right? We can track each and every single line and see how they relate to all the other lines. The details of finding a prime factor f of n is not specified here. Okay, we are just saying that we need to do that, but I'm not quite sure how to do it. It's just like when you're writing an English paper, you always have introduction and summary being the first and the last part of any type of paper that you write, right? And then inside, you usually have what? What else do you have to put into a formal English paper?
Conclusion.
Okay, you have introduction, you have conclusion / summary, and what goes in
Body.
the body. So within the body, let's say you're making an argument. Okay, you're making a point. You're making an argument. What do you need?
Main ideas.
Evidence or support. Okay,
Support
so you start with
Claims.
support, or you start with what do you start with first?
Claim.
Okay, you start with the claim, and then what do you and then next would be what? Support. Okay, support evidence, and then argument. Right? You have to somehow link the support, the facts to the point that you're making. Yep. Go ahead.
You also have a review, an argument.
Okay, so you need to review. Review.
Oh, review.
The argument.
Provide an argument against your own argument.
Oh, okay,
And
so
then
counter argument.
show
You
why
want, you
that's
want to
not
show
right.
why the counter argument does not stand. Yep. Given the evidence that you have presented. Okay, but does that have anything, so do you start with the details? I mean, by the time you start with all the evidence, like, okay, according to this new paper, year, blah, blah, blah. When you start with your paper, entire paper, do you start with all the details?
No.
No. And for the same reason, we don't want to deal with how the specifics or how to find the prime factor f of n. We just kind of say that we need to do that, but we'll defer the details or the specification of the details to a later point until we are done with this algorithm as a whole. It's just like when you do the outline of an English paper, you do the entire outline first. You don't stop with one item of the outline and say, hey, I want to drill into this one right now and do more things with this. Because at that point, you're going to lose track of the entire paper. Okay, so you need to finish the entire framework of the whole paper first, and then you look at one section and say, okay, now, how do I chop this down into smaller portions? It's the same way here. Okay, so that's why that was a really good question, because it really is the essence of top-down design. It's deferring the details to be specified later. All right. So now that we have procrastinated enough, we'll have to actually go ahead and deal with this problem here, finding a prime factor f of n. Okay. So that becomes our new problem. Now we have to write an algorithm to find a single prime factor f of n. We don't have to deal with the loop to deal with all the prime factors anymore, because it's already taken care of by revision 4b as my main algorithm. So now my focus is really just, okay, if I give you a number n, can you give me a prime factor of that particular number? How do we do it? Now we can focus on this one. Yep.
Don't you find something that has a remainder of 0?
You have to keep testing until you find a divisor that will give you a remainder of 0. Correct. Okay, that is correct. So the first thing we want to do is to do it by hand first. Now in this case, we have to use something that's more difficult, because if you say find a prime factor of 20, it's not going to be helpful, because we have all sorts of rules of thumbs to help us with this to help us with this. So it's not going to be helpful. You cannot just say, oh, it's an even number, it's divisible by 2. But how do you express that in an algorithm? It's not easy. And for the same reason, if you pick anything, even for, let me pick a number here, 91, which does not seem to be a very easy one to deal with, but if you remember your multiplication table, you can quickly identify and say, oh, 91, one prime factor of 91 is 7, the other one is 13. Okay? Well, it doesn't really fall into your multiplication table, but most of you'll know that 91 is not a prime number, and you know its factor. So you have to do something that is a lot more difficult in order to figure out a systematic way of doing it. So we can start with 2, 0, and just add a whole bunch of numbers next to it. Okay, need to double check to see whether this is nope, this won't work. That might work. Okay, so this would be a good number to start, because this way it forces you to use a systematic way to do it. All your usual rules, your rules of thumb, cannot work with this one. Okay, it's not divisible by 2 because it's not an even number. It's not divisible by 3 because if you add up all the digits, the sum of the digits itself is not divisible by 3. It's not divisible by 5 because the least significant digit is not 5 or 0. So all your usual tricks have run out already. Now you have to do it more systematically. Now when I say systematically, I know that we're looking for a prime factor, so can I just start with any prime factor like 101? Would that be a good number to start? And then I go back and try 13, and then maybe I'll try 53, and then 23.
Throwing darts again.
Yep, I'm throwing darts again, right? So it's hard for me to keep track of what numbers I have tried already, which ones I have not tried, and there's no way to really specify in an algorithm in a step-by-step fashion. So what I'm going to do is something that seems, not very smart. Okay, running out of time, but I think I can still at least get this part done. Okay, so we'll use a spreadsheet. I think I have demonstrated this before using a spreadsheet. Yeah, but not for the purpose of doing this stuff. So what I'll do is I'm going to do it for the purpose of this one, which is 201753 is the number that I'm dealing with. So now I'm listing all the potential factors here. And I also look at the remainder. The mod operation is getting the remainder of a division. The dividend in this case is $1 because I don't want the row number to change all the time. The divisor does change, so it's just B3 here. Okay, so this means dividing this number by 2 has a remainder of 1. And now we can just use this approach. Okay, so this is it may not be the smartest way, but it is a systematic way. Because I'm just checking 2. 2 is not a divisor of that number. 3 is not, 4 is not. Hey, but Tack, you don't have to try 4 because we already know that 2 is not a factor. 4 cannot possibly be a factor either. Well, you're absolutely right. But if I have to skip 4, 6, 8, 9, 10, 12, 14, 15, all the composite numbers, the logic to skip all the composite numbers by itself is difficult because nobody gave me a table of all the prime numbers to begin with. Okay, so I think it's just easier to test 4 because I cannot get a wrong answer. In other words, when I try to divide that number by 4, I cannot accidentally get a remainder of 0 and misidentify that 4 is a prime factor of that number. That is just not possible. Okay, so that's why, yes, it is a waste of time, but I'm going to do it because I want to simplify the logic of the algorithm. Somebody from the previous class, just asked me a question, about optimizing the algorithm. We can do certain tricks to make it skip certain numbers. Yes, we can, but when you're first starting to write an algorithm, efficiency should not be a priority. You need to get it right first. Okay, correctness is the first priority. The simpler the algorithm, the easier it is to verify that it is correct. Once you verify that the algorithm is correct, then you can look for ways to make it go faster. Is that making any sense? Okay, so don't shoot for making the algorithm faster and more optimized, when you're just starting on it. Even though we're testing a lot of numbers that does not need to be tested, it's not going to change the correctness of the algorithm. So just for the purpose of this discussion, let's see if we can actually find a prime factor. Yep, 23 is the first one. Okay, but I would call this fairly systematic. If a number does not work out, I just add 1 to it, and so it becomes the next potential factor of the number. Try the division, look at the remainder. If it does not work out, try the next one, and so on. Would you guys agree that this is a fairly systematic way to deal with this problem?
Yes.
Not necessarily the most efficient way, but it is definitely systematic. Okay, so on Thursday we'll continue with this, and then we'll code this into pseudocode, and then we can trace it even after that.